Hello everyone. In this video, I am going to go over the homework on counting with order. So our first question, I've made a bunch of blank space under it. We're going to make a tree diagram showing the possible outcomes of flipping a coin 4 times. So we're going to think of this as like a series of 4 decisions where we have 2 options for each decision, heads or tails. So when I start off my tree at a point, I then branch into 2 possibilities for the first coin flip. I can either do heads or tails. By the way, I'm drawing with my thumb on my screen, so please forgive my poor drawing skills. Then, regardless of whether I got a head or a tail for the first flip, I then branch again. I split into 2 for the next coin flip. So again, for my next coin flip, I can do heads or tails, heads or tails. And then after that, each of these outcomes is going to then branch again into 2 for the third coin flip. Again, please forgive my clumsy thumb drawing. So this is going to be heads, tails, heads, tails, heads, tails, heads, tails. And then one more time for our very last coin flip. Each of these is going to branch into 2. You know what? I should have just like made a computer generated one and then pretended that I was drawing it. But these are my real drawing skills on a laptop screen. Okay, so we're going to label heads, tails the whole way across. And basically, like, what you can see from this tree diagram is if you start at the very top, at the point, and then you follow one path down through the tree to the very bottom, that is like one total outcome of what could happen if you flip a coin 4 times. So for example, let me see if I can do this with a highlighter. Like for example, if I follow this branch, tails, and then heads, and then tails, and then tails, that's one possibility for flipping 4 coins. And then the point is that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 total endings to this tree here. So there's 16 different possible outcomes. All right. So for the next question, we're going to list all possible outcomes from flipping a coin 4 times in the format HHHH, HHHT, and so on, and then use your tree to help you. So the way you can use your tree is just go through and follow each path from the beginning to the end, and you can go through from left to right and just write down what the flips were along each path through the tree. So the far left one here is HHHH, and then the next one is HHHT, and then it keeps going like that. And they're actually in alphabetical order. So let me go ahead and type them here, HHHH, HHHT, oops, that's too many. And then we have HHTH, HHTT. Okay, so that was the first quarter, right? And then we have HTHH, and then HT, HT, HT. Is getting a little bit harder for me to see with my eyes. I'm like over here somewhere. HTT, H, and then HTTT. And then, okay, so was that 8 of them? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that was the first 8. If you did the first 8 correctly, there's like a faster way to do the other ones, which is just copy these and then replace the first H with the first T. Right, so I'm going to cheat a little bit. It's not really cheating, but I'm just going to make things a little bit easier for myself. So I'm just copied the first 8, and then I'm editing them to change the first flip into a T, because all the ones on the right side of the tree start with T instead of 8. And actually, we could have done a similar kind of thing, like with the first 4. We could have copied the first 4 and then pasted them here, and then edited them to, instead of having HH at the beginning, to all have HT at the beginning. So there's different like little tricks and things to list these all out. But as long as you get 16 and they're all different, and you do it in some way systematically, so you make sure you get all 16, then that's the most important part. Okay, so how many outcomes have the same number of heads and tails? And list those outcomes. So what I'm going to do is I'm just going to list all of them here, and then I'm going to cross out the ones that are not the ones that I want. So I want the same number of heads and tails. I guess that means I need 2 heads and 2 tails. So let's see, which ones have 2 heads and 2 tails? Not those ones. This one does, this one doesn't, this one does, this one doesn't. Nope, not that one. This one's good, this one's good. This one, no. No, no, no. Okay, so I found these 6. Another way that you could approach this is if you start by realizing you need 2 heads and 2 tails, you could just kind of try to think of like all the ways of arranging the H's and the T's together. This is a little harder to be systematic with, I think, but you might be able to approach it that way. It would be safer to actually just go through your whole list and pick out the ones that are what you want. Okay, so how many outcomes have more heads than tails? So again, I'm just going to go through this list here and pick out the ones with more heads than tails. So the first 3 are like that. Just paste them. Not this one. Yes, this one I do want. Let's see. Not this one, not this one, not this one. Here's one more. And then I don't think there's any more after that. It gets more T heavy as we get towards the end because they're in alphabetical order. Yeah, so I think it's just the one that's all heads, and then there's these 4 that have 3 heads. So for 3 heads, there's 4 places where you could put the T. You could put it last, second to last, second place, or in first place. Okay, so that was that. So you guys can see already a little bit of information about probability, even though I'm not explicitly asking you about probability. But you can see that there's 6 ways to get the same number of heads and tails, and there's only 5 ways to get more heads than tails. So which of these is more likely to happen? The first one. This is more likely to happen. Okay, anyway, moving along to the next question. Let me get back into internet mode so we can see this table properly. Okay, so here we have our standard American deck of cards, which is actually the French deck of cards. So each card has a suit. These are the 4 suits: the clubs, spades, hearts, and diamonds. And then each card also has a rank, which are ace through king. Each card also has a color, so the hearts and diamonds are red, clubs and spades are black. And then jacks, queens, and kings are also known as face cards because they literally have faces on them. So these 12 are the face cards. Okay, so these questions are about the standard American deck of cards, and we're going to assume that order matters, which means that drawing, for example, drawing the ace of diamonds and then the 2 of diamonds and then the 3 of diamonds, we would consider that to be different from drawing the 3 of diamonds and then the 2 of diamonds and then the ace of diamonds. Okay, and we are going to draw without replacement, which means that we are not putting the cards back in the deck after we draw each one, so we cannot repeat any card. Once that's been drawn, it can't be drawn again. Okay, so how many ways are there to draw 3 cards of the same rank? So for drawing 3 cards, I'm going to think of that as 3 decisions, and then what I'm going to do is think about how many options I have for each decision. So I'm going to lay myself out a little template of 3 numbers for 3 decisions. So first, I want to think about how many options are there for the first card. So how many options for the first card that I could draw? So my requirements are that the 3 cards be of the same rank. But before I've drawn any cards, I don't know what rank that will be. So any card is okay for the first card. I don't have to worry about matching until I'm on my second card. So I can choose any of the 52 cards for the first card. Now when I get to my second card, I don't know what my first card was, but I have to match its rank. So if we think about the idea of like drawing a tree, a possibility tree that represents the situation, I would have 52 branches for my first level. And then for my second level, I would be looking at the different possibilities that would match the rank for my first card. So for example, let's say I draw the ace of diamonds for my first card. Then in order to get the same rank, there are 3 cards left that would give me the same rank as the other 3 aces. Now, maybe we didn't draw the ace of diamonds for the first card. Suppose we drew the 5 of spades for the first card. Then there would be 3 cards left, the other 5s, that would match the same rank. So the point is that the 3 cards would be different cards depending on what my first card was, but it would be the same number of options for my second card. So it'll be 3 options no matter what my first card was. Does that make sense? I hope. So there's 3 cards going to be left that will match the same rank, regardless of what your first card was. Okay, and then for my last number here, hopefully you guys can see this is going to be 2. So after I draw 1 card, and then I draw another card that matches the same rank, then there will be 2 cards left of that rank. So let's say, for example, I draw the Ace of Diamonds first, then there's 3 aces left for my second card. And then after that, maybe I draw the Ace of Hearts next. Then there will be 2 aces left for my third card. All right, I'm hoping that this is making sense to you guys. So that's the answer on that one. And for number 6, let's try doing this. So how many ways to draw 2 cards of the same color and the same rank? So here's my little roadmap. I always color code blue the answers on these homeworks, so I have a keyboard shortcut for turning this blue. Okay, so we want to match same color and same rank. Since I didn't specify what color or what rank, any of the 52 cards is fine for my first card. If I had said, like, how many ways are there to draw 2 black queens, for example, then you wouldn't be looking at 52. But I didn't specify that. So any color and rank is okay for the first card. For my second card, now suppose that I did draw the Queen of Clubs for my first card. Then I would be looking for how many options do I have to match the same color and the same rank as my first card, the Queen of Clubs. So there would only be 1 card left at that point, the Queen of Spades, for the same color and the same rank. So this is going to be 1. And the way the deck of cards is designed is no matter what that first card was, there would only be 1 card left that would have the same color and the same rank. Okay, so it'll be 1 option left no matter what your first card was. All right, let's look at the next one. So we're going to draw 3 cards. Boop, boop, boop. Here's my little roadmap. If you're doing this on paper, I like to lay it out like this. My roadmap, when I'm doing this on paper, I usually make blanks on my paper like this. I would make 3 blanks, and then I would write 3 numbers in there, and then I would multiply them together. But for doing it on the computer, it's easier with the parentheses. Okay, so 3 decisions to make. First decision, what card goes first? So I didn't specify what suit or any properties about it, so I don't have to worry about getting different suits until my second card. For my first card, I'm just going to pick any card. Most of the problems I write are like this. Now, when it gets to my second card, I want to make sure I'm getting a different suit. So remember, the suit is clubs, spades, hearts, or diamonds. So regardless of which card I picked first, I have then eliminated all the cards in that suit, and I can't use them again. So that eliminates 13 cards. So you're looking at 52 minus 13, or you could think of like there's 3 suits left, so 3 times 13. Either way, you have 39 cards left that are going to be of a different suit than your first card. And after that, with your second card, you're again eliminating another suit, so you're only going to have 26 cards left to pick from. Hope this makes sense to you guys. And now let's try number 8. So number 8 is very similar to number 7, but it is 5 cards. So let's see if that makes any difference. Okay, so 5 cards, 5 decisions. That means I'm multiplying together 5 numbers. Okay, so I think it's going to start the same way, right? Getting different suits. So 52, 39, 26. Maybe I'll just copy, or I could just type them if Word doesn't want to cooperate with me. Okay. So after I picked the first 3 cards of different suits, at that point I've eliminated 3 of the suits, so there would only be 1 suit left to pick from. So there'll be 13 cards left in that suit. And now at this point, what are you going to do? Because you've used up 1 card, you've chosen 1 card from every suit, and there's nothing left to pick from. So how many options do you have for another card that's not one of the first 4 suits that you picked? 0. You have 0 options at this point. Your answer here is actually just 0. Oh, I think I forgot to mention this in class, you guys, but when you guys are doing this quiz on next class, I briefly mention calculators today, but you don't need to actually multiply these out. It's actually easier for me to grade if you just leave them unmultiplied. Then I can see actually how you got your answer. Sometimes it's interesting to see the big numbers, especially when you're doing probability, you can actually calculate some percentages. But for these counting types of problems, it's just easier to leave them unmultiplied, exactly like I have the answers written here. I should send you guys an email and tell you about that, I think. Okay, so for the last two questions, it's not calculations, but it's explaining. So we're still going to be drawing in order without repetition from the same standard deck of cards, and we're going to draw 5 cards. Explain why drawing 5 cards that do not all have the same suit does not meet the uniformity criterion for the fundamental principle of counting. Okay, so you have to be very careful with how this is worded, because it almost seems like it's the same task as number 8, but it's actually not. So number 8 is saying 5 cards, each of a different suit, so like 5 different suits, and that's impossible, which is why we get 0, that there's 0 ways to do this. But number 9 here, you can actually do this, because it's saying they do not all have the same suit. So it's not that they all have to have different suits, they just can't all have the same suit. So like, for example, we could have diamond, 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 club, and that would count as not all the same suit. So the words here are really important. So we can actually do this. We can draw 5 cards that do not all have the same suit. But apparently this does not meet the uniformity criterion for the fundamental principle of counting. So remember, the uniformity criterion says that if the number of options for each decision does not depend on the particular outcome of previous decisions, then you can do this thing where you just multiply together the number of options for each decision. Okay, so let's go ahead and try using the fundamental principle of counting, and maybe let's just see what goes wrong. Because usually if you can't use it, you'll actually encounter the problem while you're trying to use it. So let's see, 5 cards that do not all have the same suit. All right, well, how many options do I have for my first card? They didn't tell me what suit to use, so just any of the cards should be fine for my first card. Now let's think about how many options we have for the second card. Well, do I need to match the suit, or do I need to not match the suit? Like, should I avoid the suit that I already picked? You might be thinking maybe we should just avoid the suit of the first card, and then we can make sure that they don't all have the same suit. But if you do it like that, you're going to avoid a bunch of outcomes that would actually be included in what we're trying to count. So it's perfectly fine for you to match the suit on the first 2 cards, just as long as you don't match the suit on all 5 cards. So actually, we should put 51 here. This is fine if we get any card for the second card. Whether it matches suit or it doesn't match suit, it's fine. And we can keep just doing any card for the first 4 cards. It's only when you get to the 5th card that you have to make sure that your cards don't all have the same suit. And this is where the problem comes. Because now the number of options that you have depends on what happened during those first 4 decisions, during the first 4 cards. Because if your first 4 cards happen to match suit, all 4 of them, now you have to pick a different suit to make sure that they don't all have the same suit. But if your first 4 cards had some different suits amongst them, then at this point you could pick any 5th card. So the number of options here depends on what you picked before. So I'm just going to basically try to explain that in some words here. So we can choose any 4 cards for the first 4 cards because we're allowed to match to match suit on 4 cards as long as all 5 cards don't have the same suit. In other words, as long as they don't all match. But when we get to the 5th card, there are 2 possibilities. So if the first 4 cards matched the same suit, then we have to pick a card from a different suit. So 39 options. But if the first 4 cards didn't match suit, then we can pick any card. And that would be 48 possibilities, 48 options. Okay, so we see here that the number of options for the 5th decision does depend on the particular outcome of previous decisions. So this does not meet the uniformity criterion. Okay, now let's see what happens if we try to do the exact same thing, but with rank instead of suit. So explain why drawing 5 cards that do not all have the same rank does meet the uniformity criterion. So it seems like we just took the exact same sentence from number 9 and we only changed the word suit to be rank instead. And that is what I did. It's just rank instead of suit. Very mysterious. So let's try the same approach. We'll try using the fundamental principle of counting and see what goes wrong, if anything goes wrong. Okay, so I guess it's okay if the first 4 cards match rank. So I should be able to pick any 4 cards from my first 4 cards. And now let's see if we get into the same pickle that we did before with the 5th card. So I've got any 4 cards for my first 4 cards. Well, now don't I still have to think about these 2 possibilities? So I'm going to just kind of write the same thing that I did before, and let's see if anything happens differently. So we can choose any 4 cards for the first 4 cards because we're allowed to match rank on 4 cards as long as all 5 cards don't all match rank. Okay, but when we look, maybe instead of the word but, I'm going to use the word and because it won't actually be like a contradiction this time. And when we look at the 5th card, there are 2 possibilities. Well, either we matched rank on those first 4 or we didn't. So if the first 4 cards matched rank, okay, so like if we got 4 aces for our first 4 cards, well, now I have to pick a different rank. So how many cards would be left that were different rank than those aces? I think there'd be 48 left, right? Because I would have eliminated those 4 of that rank. So then we have to pick a card from a different rank. So 48 options. Now, on the other hand, if the first 4 cards didn't match rank, then we can pick any card. And how many cards are left to pick from? 48. So you see the difference here? In the first question, we got 2 different numbers, and we didn't know which one to put into the product. But on this one, we actually get the same number. So it is the same situation. But since we got the same number, the number of options doesn't depend on what happened with those first 4 cards, because we happen to get the same number here, 48, 48. The answer here is actually, we can do the fundamental principle of counting. In other words, just multiply together all the options on each decision, and we get 48 here. So another way to explain this would be just to note that the thing that you're trying to do is something that always happens. So no matter what 5 cards you draw, just draw any 5 cards. They definitely will not have all the same rank because it's impossible for 5 cards to all have the same rank. So that's what's different between rank and suit. Suit, you have 13 cards in each suit. Rank, you have 4 cards in each rank. And since you're drawing 5 cards, that makes it impossible for them to all have the same rank. Yeah, so since the thing that you're trying to think about doing is something that always happens, it's guaranteed to happen no matter what, then you can just use the number of ways to get any 5 cards to count the number of ways to do this. Yeah, so these last 2 questions are pretty challenging. I think I would not put these on a quiz. You can expect your quiz would be more like numbers 1 through 8. And I will see you guys in class. Send me an email if you have any questions.